Okay, third and final part. So we'll jump right in and note that we were just talking about, we know that D cannot be 0. So that means that this here is well defined. That's an important thing to note first. We're not dividing by 0. That's an important thing to know. Okay, and we also know that this denominator is not 0. Now, for convenience, I'm going to give a name to the numerator and a name to the denominator. So let's let R equal CB. Then R is an integer. And let's let, say, S equal AD. Then S is an integer as well. And S is not 0 because D is not 0 and A is not 0 for the reason we talked about earlier, right? If A were 0, that would make X 0, but X is not 0, so we don't need to worry about A being 0. Okay, so that means then that Y equals R over S, so Y is a rational number by the definition of rational. Okay, so that's nice to know, but where that's really important is we look up here and see that in our assumption we said Y is irrational. So we can say, but hold on here, Y is irrational. So that is a contradiction. Okay, so how proofs are supposed to work, right, is that if you follow all the rules and everything you're doing is either plugging in definitions that we know are logically sound or making substitutions that are according to rules of algebra, then we're never supposed to encounter any contradictions. There can't be any contradictions in the world of logic. So the only way that our whole beautiful contradiction-free logical world could come crashing down on us is if we made an assumption at some point that is false. Now, up here we assumed that there does exist some rational number and irrational number where the rational number is not 0 and the product is rational. And this was an assumption that we made, so now we know that this assumption is false because we reached a contradiction, and that can't happen in logical world unless you've made a false assumption. So, what's convenient about knowing that this statement here is false is that it is the negation of our theorem. So if the negation of our theorem is false, what does that say about our theorem, right? It says that our theorem is true. So that's the whole idea behind a proof by contradiction, is that you show that the theorem is true by showing indirectly that the negation of your theorem is false. And so we can say, because we reached a contradiction, that then the assumption that we made is false, and that means that the theorem is true. And of course, showing that the theorem is true is what we were trying to do, so we say QED, and that's an acronym for a Latin phrase that means which is what was to be shown, because that's what we were trying to show. And that completes the proof.